Welcome to a lecture on material science for BscVIsem students in 6.2 paper by Miss A.Shirly Jones, Associate Professor and Head of the Department of Physics of BscVIsem Veerashaiva College, Ballari. In the chapter Material Science, we have topics to study that are scope of material science, engineering classification of materials, engineering requirement of materials, crystalline and non-crystalline states of materials. Now, materials are the matter from which things can be made. Our earth has got huge number of materials which the mankind has used over ages. Man used rock or clay which he dug from the earth, and he has constructed houses or forts. He used dried wood products for doors, windows and furniture. He used water and air to live on. Now, materials are used after designing or engineering. Materials and the science of materials and the engineering of materials have come up together as a new branch in science called as material science. Well, what is material science? Material science is an interdisciplinary field concerned with the understanding and application of the properties of matter. Material scientists study the connection between the structure of materials, their properties, processing methods, and its preferences on applications. It includes various areas of science like chemistry, biology, biotechnology, and engineering, especially electrical engineering. Material science is the upcoming field of science where various engineering methods of new materials are used in designing and discovery of new materials, particularly in solids. Have you ever thought what the material, these TV sets, computers, suspension bridges, oil refineries, rocket propulsion, nuclear reactors, supersonic transport and many other devices are made up of? I even saw one building, an auditorium, huge auditorium built of a material, building material which can be recycled. Now, you have got organic LEDs which are very cheap in cost, and are generated in large scale. Thus, material science has given us new materials, and it is a promising field for greater research. Now, to engineer the materials are mainly classified to three categories: metals and alloys, ceramics and glasses, and organic polymers. Well, what are metals? Metals are the elementary substances which are opaque, lustrous, strong. They are good conductors of heat and electricity. And the examples are carbon, copper, lead, nickel, etc. However, the alloys are metals made up of combining two or more metallic elements. An alloy is formed by mixing of two or more metals in suitable proportions in molten form, and finally they are solidified. Individual metals have different properties, and when they are molded to form an alloy, they have a property quite different from the individual elemental metals from which they are formed. Metals and alloys find important engineering applications because of these important properties or characteristics. They are hardness, strength, rigidity, formability, mechanability, weldability, conductivity, both electrical and thermal, and dimensional. Ceramics are the articles made from clay and hardened by heat. Ceramics are compounds of metallic and non-metallic elements. Hence, there are a large number of materials which fall into this group. Examples are metallic compounds, rocks, minerals, glass fiber, and all forms of clays or ceramic substances. Now let's know about organic polymers. Organic polymers are the organic materials derived directly from carbon. They usually consist of carbon combined with hydrogen, oxygen, or other non-metallic substances. The structure of these materials is fairly complex. Some examples of commonly used organic engineering materials are plastics and synthetic rubber. Now these materials are termed polymers because they are formed by polymerization reaction in which relatively simple molecules combine to form massive long chain molecules or three-dimensional structure of materials. Now let's know about composites. Composites are a class of materials formed by the combination of any of the two or three materials, metals, ceramics, and polymers. There are many composites. First one is formed by metals or alloys and ceramics. They are combined to form composite materials like steel enforced concrete. The second one, metals or alloys are mixed with organic polymers and combined to form composite materials. For example, vinyl coated steel. And ceramics and organic polymers are also combined to form composites. For example, fiber reinforced plastics and carbon reinforced rubber. Now these materials, in order to engineer them to form the two new fabricated materials, they need certain requirements. The study of engineering materials is for the purpose of using them in some practical applications. The practical applications of the engineering materials depend upon a thorough knowledge of their particular properties under a wide range of conditions like temperature, humidity, etc. The range of properties found in different classes of materials is very large. Some of the most important properties of materials are mentioned below. The first one is mechanical properties. In mechanical properties, we need to know tensile strength of a material. It is the ability of a material to withstand tensile loads without breaking. Second one is stiffness or toughness. It is the ability of the material to withstand bending under the application of shear stresses. For example, high carbon steel will bend without breaking under the impact of hammer. Now comes the electrical properties. They are conductivity, resistivity, dielectric permittivity, dielectric strength. And the magnetic properties are permeability, coercive force, hysteresis. Thermal properties are specific heat, thermal expansion, conductivity. All these should be studied for the materials. Now the chemical properties are to be studied are corrosion resistance, acidity or alkalinity, composition. Physical properties are the beyond elementary, dimensions, density, porosity, structure. Acoustical properties are sound transmission, sound reflection, sound absorption. Now we have got optical properties or birefringence properties, which are color, light transmission, light reflection, and light absorption. Many of the properties mentioned above are determined by the actual structure of the materials. Some of the properties are exhibited by the materials because of the crystal structure of the materials, and they are known as structure-sensitive properties, and some properties are independent of the crystal structure of the materials, and such properties are known as structure-insensitive properties. Now let us know about crystalline, polycrystalline and non-crystalline states of materials. Now, you know that solids are mainly classified into crystalline and amorphous. Well, what are crystalline materials? A solid is said to be in crystalline state if the constituent particles, those are atoms or ions or molecules, are arranged in a three-dimensional periodic manner on lattice, or if it has a reticular structure. Now, in crystalline state of atoms are stocked in a regular manner, forming a 3D pattern which may be obtained by a 3D repetition of a certain pattern unit. It has a long range order and thus it has definite properties such as sharp melting point. When the crystal grows under constant environment, the external geometrical shape of the crystal often remains unchanged. Thus, the shape is a consequence of the internal arrangement of constituent particles. The ideal crystalline material has an infinite 3D repetition of identical units, which may be atoms or molecules. Examples of crystalline materials are all ionic solids, most covalent solids are crystalline, and all metallic solids are normally crystalline. Now let's know about single crystal. When the periodicity in the crystal pattern extends throughout a certain piece of materials, it is called a single crystal or unit crystal or monocrystal. Single crystals can be grown in the laboratory. Examples: rock salt, calcites, or quartz. Now, polycrystalline solids, these are the solid, or a solid is said to be polycrystalline if the periodicity in the crystal is interrupted at so-called grain boundaries. In this case, the size of the crystallites is smaller than the size of the pattern unit, which forms a periodicity. The size of the grain in which the structure is periodic may vary from macroscopic dimension to few angstroms. In general, the grains in such a solid are not related in shape to the crystal structure, the surface being random in shape rather than having well-defined crystal planes. Now, in non-crystalline states of materials, non-crystalline materials exhibit short-range order in the structure. They have neither reticular nor granular structure. When the size of the grains or crystallites becomes comparable to the size of the pattern unit, the amorphous solid or non-crystalline solid is formed. A typical feature of these substances is that they have no definite melting point, where in non-crystalline material, as the temperature is increased, they gradually become soft, their viscosity drops and begins to behave like ordinary viscous liquids. Now, amorphous solids, these have no long-range order. The atoms and molecules in these solids are not periodically located over large distances. Amorphous solids are formed when liquids are cooled too quickly from the molten state to allow the subunits to arrange themselves in the low-energy crystalline state. Some examples are silica can form either covalent amorphous solids, usually called glasses, or regular crystal structures like crystals or calcite. Now let us distinguish between crystalline and non-crystalline states. Crystalline state or crystalline materials has long-range order that extend throughout the material, and hence they show a characteristic geometry. Examples: metals, ionic solids. However, non-crystalline state of material has no long-range order, and hence they do not show characteristic geometry. Example: rock. Second difference is crystalline materials are formed when the material in liquid state is cooled very slowly and at its melting point. In other words, they have sharp melting point. However, non-crystalline materials are formed when the material in the liquid state is cooled very fast at its melting point. In other words, they have no definite melting point. The third difference is the cooling curve of crystalline materials is not smooth but has a region where the temperature remains constant when the change of state occurs. You see the flattened part there. In non-crystalline, the cooling curve is smooth when the change of state occurs. The fourth difference is in crystalline material is formed by 3D repetition of a pattern unit, and however in non-crystalline the pattern unit has short range order. The fifth difference is crystalline solids show anisotropic property. This means the properties such as electrical, thermal conductivity, refractive index, mechanical strength, coefficient of thermal expansion, etc. different in different directions. But in non-crystalline materials, all these properties are same in all directions. The sixth difference is crystalline solids give a clean cleavage when cut with a sharp edge. However, here in amorphous solids give irregular cut due to conchoidal fracture on cutting with a sharp edge tool. The seventh one is covalent solids formed by slow cooling process. However, here in non-crystalline materials, covalent solids formed by rapid cooling process usually form amorphous solids. Thus, the new materials fabricated, their structures, their properties are studied, they are used, they are fabricated or designed to form new materials which can be used for greater purposes. The field is on and the research is going on in order to find or design more and more new materials. You too can do that. Thank you.